All right, so today we're taking a deep dive into black holes. More specifically, black holes and time travel.
Yeah.
Our listeners sent in some pretty incredible research articles and papers on this topic. I'm excited to jump in.
Me too. It's a fascinating question. It really captures the imagination. Could these, cosmic monsters actually be gateways to the past or the future?
Yeah, I mean, every time you think about it, it's just kind of like, whoa, how could that even be possible? But I guess before we get ahead of ourselves, we should probably talk about what black holes actually are.
For sure.
Like, we always hear these descriptions about them being objects that are so dense that not even light can escape their gravity.
All right. And it all starts with Einstein's theory of general relativity.
Okay, so Einstein general relativity.
Yeah. So Einstein basically revolutionized our understanding of gravity. Instead of thinking of gravity as just, a simple force, he said it's actually the curvature of this thing called space-time, and that curvature is caused by mass and energy.
Okay, so I got to ask, how does mass actually curve space-time? I mean, it's one of those things you hear all the time, but what does that actually mean?
Yeah, it's kind of a mind-bending concept. A good way to visualize it is to imagine a bowling ball placed on a stretched-out sheet, right? That sheet represents space-time.
Okay, I'm picturing it.
So you've got this bowling ball, and it's making a dip in the sheet. That dip, that's the curvature of space-time. The bowling ball represents a massive object, and the heavier the object, the bigger the dip, the more it warps space-time.
So black holes are kind of like taking that bowling ball and making it like infinitely dense.
Exactly. Black holes create a dip that's so deep that nothing, not even light, can escape.
And that's where escape velocity comes in, right?
Exactly. Escape velocity is the speed you need to reach to escape the gravitational pull of an object. And with the black hole, the gravity is so strong, the escape velocity is greater than the speed of light.
Whoa, okay. So even light, the fastest thing we know of, isn't fast enough to escape a black hole's pull. That's wild.
It is pretty wild. And speaking of black holes, they're not all created equal, right?
Right, there's different sizes, right?
Yeah, you've got your stellar mass black holes, which form when really, really massive stars collapse at the end of their lives. And then you've got these supermassive black holes, which are millions or even billions of times the mass of our sun.
Yeah, those are ones that are at the centers of galaxies, right?
Yep, including our own Milky Way.
It's incredible, isn't it?
It really is. And when you have something that massive, the effects on space-time are just, well, unimaginable. It would be like taking our bowling ball analogy and swapping it out for, I don't know, a small moon or something. That sheet would be seriously warped.
So all this talk about space-time is pretty mind-boggling.
Yeah.
But how did physicists even begin to figure this stuff out? I mean, were they just sitting around thinking, what if space and time could bend?
Well, there was some of that, imagining possibilities. But it's really a testament to human ingenuity. Take someone like Carl Schwarzschild, for example. He was stationed on the Eastern Front during World War I.
Whoa, seriously?
Yeah, and while he was there, he actually found the first exact solution to Einstein's equations that described a non-rotating black hole.
Wait, hold on. He was in the trenches of World War I, and he was making groundbreaking discoveries about the universe.
Yep.
That's incredible. I mean, talk about dedication.
I know, right? And the amazing thing is that his calculations, despite the crazy conditions he was in, they actually formed the foundation for our modern understanding of black holes. Pretty incredible, huh?
That's amazing. So Schwarzschild kind of laid the groundwork, but then along came Roy Kerr, and he said, hold my beer, I'm going to tackle rotating black holes.
Yeah. Kerr's solutions were even more groundbreaking, mathematically speaking, because they described a more realistic scenario. See, almost everything in the universe rotates, right?
Yeah, planets, stars, galaxies.
Exactly. So it made sense that black holes would also be rotating, and when you add that spin, it does some really interesting things to the space-time around it.
So it's not just warping space-time, it's twisting it too.
You got it. And that's where things get really wild, because that twisting, that's where the possibility of time travel starts to come into play.
Okay, so we've got these objects warping and twisting space-time. But how do we get from warped space-time to actually traveling through time? That's what I want to know.
All right, well, to understand that, we need to go even deeper into the bizarre effects that black holes have on, well, on the very fabric of the universe.
Okay, so we've established that black holes warp and twist space-time. Pretty intense stuff, but how does that lead to the idea of time travel? I mean, that still feels like a giant leap.
Yeah, it's definitely a mind-bending concept, But the key is understanding how gravity affects time.
Gravity affects time. Okay, now you're really blowing my mind.
Remember how we talked about massive objects creating a dip in space-time? Well, near a black hole, that dip is so extreme that it doesn't just warp space, it warps time itself.
Hold on. So you're saying that time actually slows down near a black hole?
Exactly. The stronger the gravity, the slower time runs.
Wow. So, like, if I were watching someone fall into a black hole, from a safe distance, of course, it would look like they're moving in slow motion.
Precisely. From your perspective, far away from the black hole, their clock would appear to tick slower and slower as they got closer to the event horizon.
The event horizon, that's the point of no return, right?
Exactly. Nothing, not even light, can escape once it crosses the event horizon.
Wow. So what's happening to the person falling in? Do they feel like they're moving in slow motion too?
That's the crazy part. From their perspective, their clock is ticking perfectly normally. They wouldn't feel any difference in the flow of time.
So it's all relative.
Exactly. It's all about your frame of reference.
So, to the person falling in, everything seems normal. But to someone watching from a distance, they'd be stuck in slow-mo forever.
Pretty much, although we never actually get to see them reach the event horizon.
Why not?
Because of something called gravitational redshift. As light tries to escape the intense gravity of the black hole, it loses energy and the wavelength gets stretched out.
So the light gets dimmer and redder.
Exactly. And eventually, the light would be redshifted so much that it would become invisible to us. So the person falling in would seem to freeze and fade away before they even reached the event horizon.
That's even weirder than slow motion. But okay, so we've got time slowing down near a black hole. But does that actually mean someone falling in has traveled through time?
Ah, that's the million-dollar question. They've certainly experienced time differently than someone outside the black hole's influence, and that's where things get really interesting, especially when we start talking about something called Kruskal-Sekner's coordinates.
Okay, Kruskal-Sekner's coordinates. Honestly, that sounds a little intimidating.
Yeah, I know. It's a bit of a mouthful. But they're really just a way to mathematically map out the warped space-time around a black hole. Think of it like, imagine you have a grid drawn on a rubber sheet. That's our normal flat space-time.
Okay, I'm visualizing a grid.
Now, if you place a heavy ball in the center of that sheet, the grid lines are going to get distorted, right?
Yeah, like stretched out around the ball.
Exactly. Well, Kruskal-Sekner's coordinates are kind of like that distorted grid, but instead of just mapping out space, they map out time as well.
So they show how time itself gets bent and twisted near a black hole.
You got it. And what's really wild is that according to these coordinates, there could be paths through space-time that loop back on themselves, forming what we call closed time-like curves.
Oh, those time-like curves. That sounds, well, kind of like time travel.
Yeah, it's about as close to time travel as we can get with our current understanding of physics. Imagine like a racetrack that loops back on itself. Normally, if you're driving on that track, you just keep going in circles, right?
Right.
But what if you had a car that could somehow bend the track itself, creating a shortcut that takes you back to an earlier point on the loop?
Okay, I think I see where you're going with this. So these closed time-like curves, if they exist, could be like shortcuts through space-time.
Exactly. They could potentially allow travel to the past.
Wow. Okay, so time travel might be possible, at least mathematically, but there's got to be a catch, right? What about all those paradoxes? Like, if I could travel back in time, what's stopping me from, say, accidentally preventing my parents from ever meeting?
You've hit upon one of the biggest conceptual challenges with time travel, the grandfather paradox. It seems like messing with the past could unravel the fabric of causality.
Causality meaning cause and effect.
Exactly. It's the idea that every event has a cause, and the effect can't happen before the cause. But time travel throws that whole idea into question.
Right. It makes my head spin just thinking about it.
And it's not just the grandfather paradox. There are other equally perplexing scenarios. For instance, what happens to information if you send a message back in time? Does it just pop into existence? Where did it come from? These are all questions that physicists are still grappling with.
So where does that leave us? Are we any closer to knowing if black holes are time machines? Or is it all just speculation? So it sounds like we're saying that time travel might be possible, but actually doing it is, well, a whole other can of worms.
That's a good way to put it. We've got these incredible theories, but the universe is full of surprises. There are still so many questions we just haven't answered yet.
Yeah, like even if these closed time-like curves exist, how would we even begin to navigate them? And wouldn't the forces involved in getting close to a black hole just crush anything we tried to send through?
Right. The technology needed to do something like that is, well, let's just say it's beyond anything we're capable of right now. And that's not even considering the massive amounts of energy that would be required. It's incredibly complex.
It's almost humbling, isn't it? We like to think we're so advanced, but then you start talking about black holes and the nature of spacetime, and you realize just how much we don't know.
It definitely puts things into perspective, but that's part of what makes it all so exciting, right? 100 years ago, people barely even believed black holes could exist, and now here we are talking about them as potential time machines.
It really shows you how far we've come. And who knows what incredible discoveries are still out there. Maybe someday our understanding of all this will seem pretty basic compared to what future generations will know.
Absolutely. We're constantly making new discoveries and refining our understanding of the universe. Every new piece of information brings us closer to a more complete picture.
So for our listeners who want to explore these ideas further, what would you recommend? Where should they go from here?
I'd say dive into the world of black holes and general relativity. There are so many great books, articles, even videos out there that can take you deeper into these concepts.
Exactly. And don't be afraid to let your imagination run wild a little.
But also, keep that scientific lens handy. We've come a long way since Schwarzschild, but the journey is far from over. Black holes still hold plenty of mysteries, and maybe, just maybe, the key to time travel is hidden somewhere within those mysteries. Something to think about anyway.
Definitely. The universe is a strange and wonderful place, and the more we learn, the stranger and more wonderful it becomes.
Couldn't have said it better myself. So, to everyone listening, keep those questions coming, keep exploring, and thanks for joining us on this incredible deep dive into the mysteries of black holes and time travel.